Okay, so the title, good evening, everyone, and it's evening in India. So, good evening. It may be good morning or good afternoon at some other places of the world. So, here I will be talking on graphene and graphene like nano dimension materials for diagnostic applications. And our institute is in Chandigarh, city of India, and we are under Council of Scientific and Industrial Research, which are government aided organization, and the vision of our institute is the instrumentation and materials for advanced applications. We work on avionics, photonics, biomedicals, and routine sensors, etc. So now coming to my presentation, this is general standard definition of nanomaterials. All are well learned experts here, so I need not to mention what nanomaterials is, but just as a formality, that any material which is in the dimensions on in the range 1 to 100 nanometer are referred here as nanomaterials. So that's why I took that graphene and graphene like nanomaterials, because the material that graphene related materials we have used in the nano dimensions. So there can be 0D, 1D, 2D, everyone we are aware of that. So we have worked on some 0D like quantum dots. We have worked on some nano sheets which come under 2D materials, and so on. Different types of nanomaterials which we work in our department or in our group are polymer based, carbon based, metal nanoparticles, semiconductors, etc. Coming to graphene and graphene like nanomaterials, in this lecture I shall be discussing the work which we have done with the graphene oxide and HBN materials, and one to work I will be presenting on chalcogenides materials which are considered in the graphene like nanomaterials. So this is just a general brief of the graphene nanostructures. These are the allotropes of carbons, and they show good electricity and heat efficiently. Another material which we have used for our diagnostic application, again hexagonal boron nitride, and this is also known as the white graphene, as it is a isomorph of graphene. Only the difference, it is made up of boron and
Suman,
nitrogen.
Dr. Suman, can you change your slides or you are in the first slide?
No, I am changing. It's not moving.
No.
Okay, just a minute. I again reshare it. Is it moving now?
Yes.
Okay.
And
So
you need to zoom out your slides because it's too larger and we can't see the above content in the slide.
okay, okay. Now.
Just more move out, zoom out. It's fine.
Okay. So this we discussed that I shall be covering graphene and graphene-like nanomaterials. Graphene oxide and HBN are the materials which we have used for our diagnostic applications, and tungsten disulfide, which comes under chalcogenides, and the graphene-like materials we have used for our diagnostic applications. So this is general. I told about that general graphene is allotrope of carbon and hexagonal lattice. It is having good conductor, and electricity flow is there. So graphene is one of the most studied till date and most exhaustively used for different applications. Here we explored it for diagnostic applications. Hexagonal boron nitride is another material which we explored for our diagnostic applications, and it is also known as white graphene. So it comes under graphene like materials, and it is isomorph of graphene. Only the thing is, it is made up of boron and nitrogen. This, as I mentioned earlier, the tungsten disulfide nanostructures are another nanostructures which we have explored for our diagnostic applications. There are a number of applications related to graphene and graphene-like materials, right from wearable devices to information processing systems. But at our group we mostly use these materials for biosensings, for diagnostics, food quality and water quality. This is what our group is dedicated to. So coming to giving some glimpse of the work which we are working at our institute with graphene and graphene like materials. And here in this presentation I have included diagnostic applications for the detection of oxidative stress biomarkers, where we have taken ferritin as it is its level in our body indicates the level of stress we are having in the body. So ferritin is the molecule which we have studied using graphene, graphene dots, and tungsten disulfides. These are some ranges which are preferred for male and female, and both imbalance in its concentration, whether it's below the recommended or above, it creates imbalance in our body. So the first work which we will be discussing is amine functionalized graphene oxide for ferritin estimation. Here we used graphene oxide and amine functionalized it with amine groups to have enough chemistries for immobilization of antibodies. Here we have used antibodies as the bioreceptors which provide specificity to our material. So antibodies for the against ferritin we have used here. And here in our group one important thing is most of the time we try to have as simple as possible the synthesis protocol. So this is only, for example, we kept the mixture at the stirring and centrifuged it, etc. And this material we used for this screen printed electrode modifications. And after a sequential modification we studied these electrodes also for change in their
That's
respective.
really apologize for that. Are you changing the slides or you are in the fifth slide?
I'm changing.
No. First, you need to, first of all, you need to cancel the privacy settings on the top of your presentation, and you can keep the presentation mode at the bottom of your screen. You can see the slide presentation in mode in the presentation mode, so that you can see the only one slide on your screen. So it will be easy for the other speakers to have a glance on your presentation, and they can understand what you are delivering your lecture.
Yes, but I was moving my slides. Anyways, let me try once again.
No, no,
सुमन
no.
Yes,
सुमन हेलो सुमन
yes.
जस्ट येलो पे जो टेक्स्ट आ रहा है ना उसको आप
हाँ,
क्लिक करिए देन ये मोड में हो जाएगा ये जो ऊपर की ओर देख रहे हैं ना
yes.
रेड है एडिटिंग इसको क्लिक कर दीजिए आप देन आप इस पे आइए जो अपना स्लाइड शो मोड है क्योंकि ये येलो यहाँ पे हाईलाइट हो रहा है देयरफॉर इट इज नॉट शोइंग द चेंज इन द स्लाइड आप तो कर रहे हैं लेकिन वो दिख नहीं रहा है अब करिए आप
Now
वो चला
moving.
गया ना नाउ यू कैन प्रोसीड अगेन
Now moving.
हाँ यस but put it in presentation mode.
It is in presentation mode from my side.
Uh, okay, maybe some technical problem can be, but now it is changing.
Okay. So till here, I discussed that we used graphene oxide and functionalized it with amine groups for ferritin estimation. Then, before using for any sensing application, we characterize the material for their optical and other spectroscopic properties and electrochemical properties, whether the material is suitable or not. So here we presented the UV spectra of aminated graphene oxide, amine compound, and graphene oxide, and we could see the sequential changes in these materials after modification with amine. Similarly, FTIR spectra also showed the presence of amine related linkages. So we used this material for ferritin detection using microfluidic setup. Here we designed this is the work which which we did with the Hull University, and all these microfluidic flow devices were made there. One of my student visited this university for his PhD fellowship. And here we use syringe pump for continuous flow of our bioreceptors and biochemicals on the chip. This is the chip which we have integrated. And this is the close view of this chip, and recorded the electrochemical signal generating from the flow of chemicals over it. So here our system could give the linearity between 7.8 nanogram to 500 nanogram only. And pH effect also we studied. We flowed different buffers and recorded the response in presence of these buffers, and we could see that at pH 7.5 and 7 we get the optimum results. So we concluded all our studies at pH 7.5. Reproducibility, we used five electrodes similar prepared identically, and we recorded their performance. Interference studies also we did with the bovine serum, myoglobin, hemoglobin. These were the biochemicals which we are having, and these are identical. Like hemoglobin is it's also iron related, anemia related molecule. So ferritin, we recorded the response in ferritin, then ferritin and hemoglobin, ferritin and myoglobin, and ferritin BSA. So almost no interference was observed from these chemicals because this is the immunosensor which where we used antibodies as the selective bioreceptors. Another in this work, this was published in ACS Applied Nanomaterials in this year only. Here we use graphene quantum dots and methyl orange composite for ferritin detection, and this work presents optical detection of the ferritin. And again, as I mentioned that we emphasize on the simple synthesis process, so here we opted for the hydrothermal treatment followed by probe sonication, probe sonication and then hydrothermal treatment. So this is very simple process, no very hardcore chemicals, harsh chemicals have been used. And methyl orange and graphene quantum dots, this couple provided a very good optical properties. And in this case, graphene quantum dots, they flourish, and in presence of antibodies, when we attach the antibodies, this emission stopped. And methyl orange also stopped this emission, but when we put antigen, this antigen replaced methyl orange and its emission also regained. So this is the phenomena which we try to track for ferritin detection. As I mentioned, this is just a simple synthesis sonication followed by hydrothermal process and sample collections. These quantum dots were also characterized for their morphology, for their optical properties, for their crystallinity, and this the TAM study showed that these are into 1 to 2 nanometers of dots which have been synthesized. Then this is the UV spectrum and PL spectrum, that absorbance at 365 followed by emission at 460 nanometer. FTIR also showed the presence of functionalities, and the data was recorded as a function of excitation, and we could see that the signal is not deviating from its position. This shows that our quantum dots are quite stable. In this case, we could attain the linearity from 10 nanogram to 4000 nanogram, uh, and R square of 0.99. Similarly, here also pH and temperature study we performed, and temperature in pH in alkaline in acidic pH, there the peak this peak got exhaustively shifted to the lower wavelength, whereas at other pH it was almost at the constant positions, and with the maximum response at 7 pH. Temperature affected because these biomolecules are very prone to temperature fluctuation. So we studied this temperature from 20 to 45. So from 20 to 30, this material is stable because antibodies or other bioreceptors, they could resist only this much change. So whenever we are not using these electrodes, we need to store it in the refrigerated conditions. Again, reproducibility and interference studies we did with the hemoglobin BSA and streptavidin. This is another work where we used tungsten disulfide quantum dots, and here also we used them for the electrochemical ferritin sensing. And important part is the biosurfactant. It is the biosurfactant stabilized. So it's a sort of green technology. We can say that we have not used chemicals to stabilize these tungsten disulfide. And here again, our motive was to have minimum chemicals usage, so we opted for probe sonication. And here also we used ferritin antibodies for detection of ferritin. Screen printed electrodes which are easy to use. We have used screen printed electrodes for ferritin detection and monitored the immunocomplex formation in presence of ferroferricyanide. As mentioned, this is the synthesis of our material and its characterization, where we recorded HR, time, EDEX, and we did elemental mapping. We showed the presence of all elements, sulfur, tungsten, oxygen, carbon. Then, as FTIR also showed the presence of CS stretchings, NS stretching. These stretchings help in providing again the binding efficiency for antibodies. And electrochemical characterization also we performed just to check what is the effect these sequential modifications are having on the final electrode. And in this, that linearity range was in micrograms. It was less as compared to the previous studies. It was sorry, this is the antibody concentration. We varied from 5 microgram to 2 microgram, because we don't want to use too much antibodies also to make it economic. Antibodies, they cost a lot. Electrochemical sensing resulted in linearity of 10 nanogram to 1500 nanogram. And here we used both the differential pulse voltammetry and cyclic voltammetry just to see is there any change in the sensitivity of the electrodes. And we could see that differential pulse voltammetry gave better R square value. So further studies, for the comparison, we studied these two techniques. pH effect, at pH 8 the signal got reduced, so most of the reactions are comfortable at pH 7 to 7.5. This is white graphene quantum dots, which I discussed in the starting, and this work was published in Faraday discussion. Here, these white graphene quantum dots are very less explored for this electrochemical sensings, but we tried, because and we took quantum dots of white graphene. And the same here also, our motive was the simple synthesis, so sonication and the heat treatment was sufficient for its synthesis. The respective TAM, UV, PL characterization, and here also the PL shows that our quantum dots are quite stable, as its peak remained, emission peak remained at the constant position with the change in excitations. For the electrochemical detection, here characterization, we used impedance to see their electrical conductivity. And ferritin sensing also we did using impedance spectroscopy, and in this case we got the linearity from 10 to 2000 nanograms. These are interference and reproducibility studies, and here we used avidin, BSA, ferritin, and hemoglobin. And here, 5 electrodes, we measured the response of these 5 electrodes prevailed in the identical behavior. So, final overall comparison, if we study of these platforms, we used aminated graphene oxide, we used quantum dots, graphene quantum dots, HBN quantum dots, and biosurfactant stabilized tungsten disulfide. And we could see that the best linearity was obtained in the GQDs, the graphene quantum dots, and pH range was almost identical for all these studies, but most efficient this platform was graphene quantum dots, which has been proved. And all this work has been published in good impact factor journals. That's all from my side. Thank you for your attention.
Thank you for your presentation. Any questions for Dr. Singh?
Yes, I want to know someone. Can
Yes.
we use amperometry for sensing application?
No, in these studies we have not used amperometric, but yeah, we are working on another developing a point of care device for cardiac biomarkers. There we have developed a portable handheld device just like a glucometer, and that there we are using amperometry. Here we have used only cyclic voltammetry, differential pulse voltammetry, impedance, and fluorescence.
In differential pulse voltammetry, first you make the calibration curve.
No, calibration curve we do when we prepare this different concentration studies, that we need to do. for to study the linearity efficiency of the system.
Okay. For otherwise, for a specific sensing, you don't need a calibration curve.
A calibration curve we need when we go for these unknown samples. When we do with the real samples, of course real samples are difficult to get, so we generally do with the spiked samples. So for spiked samples you need that calibration graph.
Okay. Thank you.
Thank you.